we're going to talk about Newton's second law. Newton's second law is most famously expressed in terms of F net is equal to ma. The net force on an object, all the positives minus all the negatives, is equal to the mass of an object times the acceleration of that object. The net force causes the acceleration. Different books will express this in different ways. I prefer to express it as F net, like that. This book actually expresses it as sigma F. That sigma is a summation symbol, so the sum of the forces is equal to the mass times the acceleration. Depending on which high school teacher you had, or if you didn't take this in high school at all, then you might have different preferences on which one you think is easiest. I tend to think that saying F net is the easiest thing because it doesn't require you to draw that funny looking E or sigma, and you don't have to remember any Greek letters when you just write it as F net is equal to ma. However, both of these things mean the exact same thing, either taking the net force or taking the sum of all the forces. That literally means the exact same thing. The units of force is newtons, as we discussed, the units of mass is kilograms, and the units of acceleration is meters per second squared. Again, as we discussed in the last part. I've got a question for you. You accelerate in your car at a green light. Your car has a mass of 1,200 kilograms, and your acceleration is 4.5 meters per second squared. What is the net force on your car? This is one of those handy cases where it's super easy because you can just plug things in. This is not really physics right here. This is just plugging things in. Sometimes I have to include these kinds of example problems just to prove to people that it really is exactly as easy as it looks. So you plug in 1,200 kilograms in for m, you plug in 4.5 meters per second squared for a, and you multiply them together and you find F net, which is 5,400 newtons. Excellent. Forces, of course, don't have to act in one direction at a time. You can have forces in multiple directions. You can have multiple forces, each acting in their own direction. And so we have to complicate this a little bit. In kinematics, we talked about acceleration in x and acceleration in y. We had a bunch of example problems where you had some object flying through the air in free fall. That's great for objects that are in free fall when there's only that one gravitational force acting on an object. We are now examining possibilities where there could be multiple forces acting on one object, giving it accelerations in x and accelerations in y at the same time. With objects in free fall, the acceleration in x was 0. This ax was 0, indicating there is no net force in the x direction. That's because there's probably just no forces acting in the x direction. F net y, that is for what's happening in the y direction, and we remember that the acceleration in the y direction in free fall problems was negative 9.8 meters per second squared. That can tell us what the gravitational force in the y direction must be. There's not going to be a gravitational force in the x direction, after all. But now we can look at these things through a different lens and say, well, what if I'm pushing on the object in a weird direction and actually physically making it accelerate in both x and y? If I can take my force, the force that I am exerting, the net force that's being caused on the object in the x direction. Now, this is going to involve some trigonometry. You might have some trig that you need to do to find what the net force is in the x direction, but then you can use that to find the acceleration in the x direction. Likewise, you use some trig to find the net force in the y direction and use that to figure out the acceleration in the y direction. So, for an example, in empty space, I push a 100 kilogram satellite with 5 newtons of force at an angle of 30 degrees above the x-axis. What is the satellite's acceleration in x and y? Here we've got a satellite. There, that's a satellite. And we're pushing it at an angle of 30 degrees above the x-axis with 5 newtons of force. And the satellite has a mass of 100 kilograms. Then we can find the acceleration in x and y on that satellite. There are 2 ways of going about this, and I'm going to show you the conceptually easiest way. I can break up this 5 newtons of force into an x component and a y component. Let me redraw the 5 newtons of force. There's 5 newtons. And then there's the x component, and there's the y component. There are 2 components to this force because it's acting at an angle. And so you can break up that force into x and y. This, if this is still giving you problems, then you definitely need to read that part of the textbook. It's approximately section 1.7. We can break this up into an x force of 5 newtons times the cosine of 30 degrees. And this can be 5 times the sine of 30 degrees. Then we have F net x is equal to max. There's only one force acting in this entire problem, and it is this applied force from pushing the satellite up like that. And so the net force in the x direction is going to be just that force, its x component. So we can take the x component of our only force, and we plug it in here. 5 cosine 30 is equal to the mass times the acceleration in x. But 5 times, I need my calculator, the cosine of 30 degrees. Oh, I don't need my calculator. I know that. 0.866 is equal to the mass, which was 100 kilograms, times the acceleration in x. So 5 times 0.866 divided by 100 gives us that acceleration in x is 0.0433 meters per second squared. We can do the exact same thing with y. F net y is may. Our force in the y direction is there. So I can bring that up here and say that 5 sine 30 is equal to may. 5 times the sine of 30, 5 times the sine of 30 is 2.5, and that's equal to 100 times ay. So divide that, and you get that ay is 0.025 meters per second squared. Now we have the acceleration in x and the acceleration in y. We can find the total acceleration if we wanted to. It would be that squared plus that squared, take the square root, and you can calculate that on your own if you wish. The alternative way of doing this problem is actually to start by finding the acceleration. You just say, you know what, I'm going to define a weird axis in that direction. I'm going to call it the A axis or something. I'm going to find the acceleration along that axis, and then I'm going to break that axis up into the x and y components of that. That's the alternative way of doing that. This is the conceptually easiest way of doing that problem. I give you the answers there again, and it's what we just got, fortunately. Instead of two-dimensional forces, what if we have a case where we have 2 forces acting on an object? there are many different ways of having two forces acting on an object, and I figured that we could have a little bit of fun with this case. So let's assume that the force of air resistance, we're actually going to do a question that has a little bit of drag in it. I wanted to show you what a question with drag in it looks like so that you know that in the future you're not going to be facing very many of these. If you can see what a question with drag looks like, you'll be able to tell, oh, this question does not involve drag because it does not have this right here. If we ever do a question with drag, I will tell you that, and when I say drag, I mean air resistance. If we've got a question with air resistance, I will tell you that the force of air resistance is equal to something. And so here, the force of air resistance is equal to 0.32 times the velocity of the skydiver squared. If the skydiver has a mass of 80 kilograms, find the terminal velocity of the skydiver, where terminal velocity is the velocity at which the skydiver no longer accelerates. That's what we're looking for. We are looking for the velocity at which the skydiver no longer accelerates, assuming that the force of air resistance is 0.32 v squared and the skydiver has a mass of 80 kilograms. And just from this, we can actually find all of that. Here's our setup. We have a skydiver right there. We've got forces acting on the skydiver. We've got two forces acting on the skydiver. We've got the force of drag or air resistance, which I said is equal to 0.32 v squared. And presumably that's pointing up. If the skydiver is falling down, then the force of air resistance is pointing up against the direction of motion. The force of gravity is the thing that's pulling the skydiver back down to Earth, and that is always equal to the mass of the object, the mass of the skydiver, times the acceleration due to gravity. This force we can just calculate out. The mass of the skydiver, I said, was 80 kilograms. The acceleration due to gravity is 9.8 meters per second squared. Therefore, the force of gravity acting on the skydiver is 784 newtons in the downward direction. If we have drawn that a force is going downward, we can just write the numerical value of the force, because the direction here tells us that, oh, it's actually negative, really, because it's going down, but we've just drawn that as an arrow rather than putting an extra negative sign there. The question is, at what velocity is acceleration equal to 0? We start with the net force is equal to the mass times the acceleration. It's good to look at a problem like this and say, okay, what directions am I looking at? Well, am I looking in X, back and forth like that? Probably not. I don't see any forces acting in the X direction. Am I looking in Y? Yeah, probably. I've got forces acting up and down in the Y direction. So this is definitely going to be Y forces. Not that it makes much difference, but it is convenient to know that there's nothing going on in X. What can we do? We can replace the net force with all of the positives minus all of the negatives. This is what I'm wanting you to be able to do on your own. This is another thing that people need to get to develop some skills on. The net force on an object, just like your net income is all of your income minus all of your expenses, your net worth is all of your bank accounts minus all of your debts. Take all the positives minus all the negatives. All the positives, well, there's just one positive. It's the force of drag, the air resistance. So I'm going to write that, all the positives, right there. Subtract off all the negatives. Well, there's only one negative. It's the force of gravity. So all the positive forces added up together. Well, there's only one. Minus all the negative forces added up together. Well, there's only one. So force of drag minus force of gravity. And that is your net force right there. So the way that I usually solve these equations is I take one side at a time. I'll take this side and say, okay, this side is equal to this, and this side is equal to this. I'll just kind of go down like that, you know, keeping the sides on the same side as much as possible. Mass times acceleration, well, I'm saying acceleration is 0, or more specifically, I'm looking for when or at what velocity the acceleration is 0. So I'm just going to set acceleration equal to 0 and solve as much as I can with acceleration being 0 and see where that leads me. What can I do from there? Well, I can start plugging in numbers. I told you that the force of drag is 0.32 v squared. So the force of drag, 0.32 v squared. The force of gravity we already calculated to be 784 newtons. And so I can plug that in there. The mass is 80 kilograms, but the acceleration is 0, so it's all equal to 0 over there. I can do a little bit of algebra, add 784 to both sides. That gets the 784 to be positive over there. 0.32 v squared is equal to 784 newtons. I can then divide both sides by 0.32. V squared is equal to 2450. Then I can take the square root, and I find that the terminal velocity of this skydiver must be 49.5 meters per second. If I go all the way back here and plug in 49.5 meters per second in to the force of drag, or plug it in there, square it, multiply by 0.32, subtract 784, I'll get 0 net force, and therefore the skydiver will no longer be accelerating. The skydiver will just be falling down at a constant rate when the skydiver hits terminal velocity. Newton's third law. For every action, there's an equal and opposite reaction. That's the classical way of saying this. For any force from object A to B, there's a force from B to A with the same magnitude and opposite direction. I'm getting a question. Wouldn't it be negative since he's falling down? Oh, the velocity. Yes, we probably should say that the velocity for that skydiver would be negative. It's implied that he's falling down from the question, but yeah, you're probably technically right. We should say that it's a negative velocity. We can either say a negative velocity, or we can say he's falling down at 49.5 meters per second. Great. Okay, back to Newton's third law. Easiest way to understand this is through some examples. I've got a book on a table, like that. Book on table. When you're looking at Newton's third law, you should be looking for third law pairs. That's what we call them. For every force acting on an object, there's going to be another force acting the opposite direction from the opposite object. If you have a book on a table, let's just look at the book on the table. Well, the forces acting on that book, on that table, is the normal force pointing up and the force of gravity pulling down. They just so happen to be the same because the book isn't accelerating, but that doesn't really matter for Newton's third law. Whether or not something is accelerating does not matter for Newton's third law. Now, let's make a free body diagram for the table instead. Instead of the book, we're going to make a free body diagram for the table. And we're only going to really include the forces from the book on that. So think, what are the forces acting from the book on the table? Well, the book acting on the table is going to have another normal force. If you drop something on some other object, well, the table is having to push up on the pen, but the pen is pushing down on the table. If you take a very, very heavy book and drop it on the table, you can tell that the book is pushing down on the table with a bunch of force. So the book acting on the table is going to have a downward normal force on that table. If we make the free body diagram for the table, we see that the book is pushing down on the table with a normal force of its own. The normal force from the table on the book is the same magnitude but the opposite direction of the normal force from the book on the table. So table on book, book on table. I should say table acting on book, book acting on table, like that. Same type of force, both are normal forces. Same magnitude of force, completely opposite direction. That is the meaning of the expression for every force there's an equal and opposite force. We can have another example, which this example really annoys people. We've got a book just sitting on Earth. You just drop the book on the ground somewhere. Obviously, the book is being attracted to the ground by the force of gravity. There's also going to be a normal force acting on the book, keeping it from falling through the Earth. But we're going to ignore that stuff for now, and we're just going to look at, okay, the book is trying to get pulled through the Earth because of the force of gravity acting on it. Well, that is the force of gravity acting on the book. On the other hand, if we look at the Earth, it turns out that the book is pulling up on the Earth with its own gravity. Anything with mass has a gravitational field about it. And so a book has mass, and so it's pulling on everything around it. Obviously on Earth, that gravitational pull doesn't matter very much because there's so many heavier things on Earth. But if these were the only two objects in the universe, the Earth and the textbook, then it would be a fairly significant effect in the universe. And that means that the Earth is going to be attracted to the book because of the book's force of gravity. The book is attracting the Earth with its own gravity, and the force of gravity of the Earth acting on the book is equal to the force of gravity of the book acting on the Earth. That part right there really annoys people, that the amount of force of Earth on the book is the same as the amount of force of the book on the Earth. The book is pulling on Earth with the exact same amount of force that the Earth is pulling on the book. That annoys people, and that's okay. Obviously, the book is going to move a whole bunch more than the Earth, because remember, F equals ma. The mass of the Earth is a whole lot more than the mass of the book. So if you have a very large mass and a certain amount of force, then the acceleration will be very low. If you have a very low mass, like a book, and some amount of force, then your acceleration might be a whole bunch. So the difference in mass of the Earth and the book, that causes the difference in the accelerations of the Earth and the book in this case. It's the exact same force of the Earth acting on the book or the book acting on the Earth, but because the masses are so different, that's why dropping a book on the Earth, well, it looks like it's just the book accelerating, which to a first approximation is totally correct. If we have another example, this will be the last example for the day. We've got a block pushing another block. So the example is we have got two blocks sitting on the floor in contact with each other. Block A has a mass of 10 kilograms and block B has a mass of 15 kilograms. You come in and you push block A with a force of 75 newtons. Determine all of the forces on block A. This question is effectively asking you to make a detailed free body diagram for block A with the values of each force. If we've got a 10 kilogram block, block A, a 15 kilogram block, block B, a force of 75 newtons pushing on block A, that's from you, pushing on block A. We need to find all the forces on A. If we make a quick free body diagram, we can say that there is a 75 Newton force pushing on the block. There's the force of gravity trying to pull it down through the table. There's the normal force preventing it from falling through the table. And there's a force from block B saying, I don't want to get pushed. And if you push on a wall, then the wall pushes back on you. If block A is pushing on block B is therefore pushing on block A. And so there has to be a force from block B. That force is a normal force, fundamentally. The force from block B on block A is a normal force because they're in contact with each other, but we're just going to call it force B for now, which also is the way that we abbreviate magnetic force. So you see that physics is incredibly inconsistent with its own naming conventions all this time. Physics is consistent in math, but not in naming. And so we can change subscripts at will, and you just have to be able to read the subscripts and say, was there a magnet acting on this? No, there's no magnets here. So we're going to assume that that's not the magnetic force. Is there any water? Is this like buoyant in water? No, so there's no buoyant force. So this must just be the force from B acting on A. B, train yourself to be able to do that as much as possible. We could add friction into this as well. However, I didn't actually give you any information about friction. If you are given a problem with absolutely no info on friction, that probably means that it's a frictionless problem. If you're not given friction and you're not asked for friction, then assume that we're in a frictionless environment. And so because I didn't give you anything about friction, and we haven't even really talked about friction except conceptually, then we're going to assume that this is a frictionless environment. What do? We can first start looking at the normal and the force of gravity. So we can use Newton's second law to figure out the value of the normal force and the force of gravity. We can write down Newton's second law in the form of F net y is equal to ma(y). F net y is all the positive forces minus all the negative forces. Well, we're looking in the y direction, so I'm going to cover up all the x things. We've got normal pointing up, and we've got gravity pointing down. And so I can replace that with all the positives minus all the negatives. And so that's going to be all the positives minus all the negatives, because the normal is up, force of gravity is down. Question, I'm giving you the answer right here, but you should be able to answer this on your own. What is the acceleration of block A in the y direction? In the positive or in the up or down direction, is block A accelerating? Is block A going to start going like that? Or diving through the table like that? I'm going to guess no, that there's no acceleration of the block in positive y or negative y. The block is going to be sliding across the table, but not moving up or down into the table. Therefore, the acceleration in y must be 0. So we've now taken our Newton's second law equation, F net y is equal to ma(y), and we've broken it down. We've broken this down into all the positives minus all the negatives. And we've said, oh, I know the acceleration in y, it's 0 because the block isn't leaping up or going down. Do a little bit more algebra on that, and remember that the force of gravity is mass times gravity, and you can figure out that the normal force has to be 98 newtons up, and the force of gravity has to be 98 newtons down. So that'd be a positive 98 and a negative 98, and they'd cancel each other out, and you'd have no force going up or down. Remember, this is a 10-kilogram block, so 10 kilograms times 9.8 meters per second squared gives you your force of gravity, and you can use that to also apply the normal force. For force B, we also need to use Newton's second law. We know that the total mass of all this going on here is 25 kilograms. Total mass here is 25 kilograms. And I'm pushing both of them I'm pushing on A, but that is pushing both of them. I'm pushing with 75 newtons of force. Think to yourself, do you think that the acceleration of A is going to be more than, less than, or equal to the acceleration of B if you're using A to push B along? If you're using A to push B along, then the acceleration of A should be equal to the acceleration of B. If B was accelerating faster than A, then A would start out moving and B would like suddenly jump across much faster than A. If B was accelerating slower than A, then A would end up going faster than B, and B would have to like phase through object A and pass through it impossibly. So the acceleration of A has to be equal to the acceleration of B. We know that the total mass is 25 kilograms for all that, and we're applying 75 newtons to all of that. We can take F equals ma, and we can say 75, that is our net force on everything put together, 75, is equal to the mass of everything put together, 25, times the acceleration. We solve for acceleration, we get 3 meters per second squared. Excuse me. And then we can say, oh, the accelerations of each of these is 3 meters per second squared. I can then use Newton's second law again on object A. So what do? I say that A pushes B with 15 times 3 equals 45 newtons. This is the mass of B times the acceleration of B. I know that for B, it is accelerating at 3 meters per second squared. And so that goes in there. I know that the mass is 15 kilograms. That goes in there. And so I know that the force pushing B forward must be 3 times 15. 3 the acceleration, 15 the mass. The acceleration on B must be 45. The acceleration must be 3 meters per second squared. The force on B must be 45 newtons. Therefore, B, if A is pushing B with 45 newtons, then B must be pushing A with 45 newtons by Newton's third law. And if B is pushing A with 45 newtons, then that's that right there, 45 newtons to the left, like that. This is how we can find all the forces acting on an object in this kind of case.